Hey everybody, this video is going to be for the Titrations lab, but first I wanted us to get familiar with some of the glassware we're going to be using. So we've got a beaker, a flask, a graduated cylinder, and a burette. This is the piece that we really want to focus on because it's special for titrations. Beakers are great for carrying liquids. They've got a nice pour spout, they've got a good wide opening, but the measurements on the side are really inaccurate. So we don't use them for measuring, but for getting amounts of liquid we're planning on using. Flasks are designed for things to be swirled in them. They've got that nice angled side, so that way you can swirl reactions in them. So we're going to be using this for most of the reactions where we're mixing things. Graduated cylinders are designed for measuring liquids more accurately. So if we need to measure something down to a half a milliliter or 0.2 milliliters, graduated cylinder would work. And you can see the numbers on the graduated cylinder start at 0 and count up. A graduated cylinder is designed to be empty and to be filled up and measure how much liquid you're filling it with. That is important for when we're considering a burette. Now, it's a little hard to see, but a burette's numbers, 50 is at the bottom, and up here at the top is the 0. So burettes are designed for measuring how much liquid is coming out of them. So burettes are designed to be full and then to be emptied out, and you can measure very accurately how much liquid you deliver by turning this, this valve here and letting liquid out. So this is what our experimental setup would look like. We've got our flask at the bottom. It's got our the thing we're analyzing. In this case, it is a little bit of vinegar, which has acetic acid in it. And then in the burette, we've got the thing we're titrating with. That's going to be sodium hydroxide in this case. And most of the time, I'll be pretty zoomed in. But all you do is you add some amount of liquid. And as you add liquid, you can measure how far down it goes. It starts, we had it filled up to 0, and then as it counts down, we'll count how much is delivered. Now, one of the important things about this is we're dealing with adding a clear liquid to a clear liquid. So in order to make it so we can actually see the reaction, we're going to add our favorite indicator, phenolphthalein. Phenolphthalein will make it so we get some visible color change as we do our titration. Now I'm just going to let this run quickly. As the base goes into the solution, the base reacts with the sodium hydroxide as base, reacts with the acetic acid in the vinegar, and that is going to create water and sodium acetate. And as that happens, we could stop it at any point, and there's some amount of acid that's been reacted depending on how much base we put in. So we can't tell how much, though. We don't have any indicator. We don't have any visual change there. And what the indicator allows us to do is it's going to change colors when our solution in the bottom goes from acidic conditions to basic conditions. So as the acid gets used up and stops being our excess, so again, if we stop it, the acid is in excess, we're still in acidic conditions, and then we keep adding base. And we want to find that point where the acid and base have equal numbers of moles. And you can see some of that pink color starting to show up as we start to get close to the point where it's reacting, and you can tell we're ignoring a lot of things here. We've got some asymmetry in where the reaction is happening, but it does go throughout the entire solution eventually. And as we start to create a more localized basic location, we can see that pink start growing larger and larger. It actually looks really cool. And once we get a persistent pink, because we don't want to just react the acid in one spot, we want to react the acid in the entire flask. So we're going to wait till we get a nice consistent pink. I'm going to stop. It looks pretty pink, but if I give it a swirl, you'll notice once we get mixing in there, we haven't reacted all of the acid yet. Oh, I'm going to stop. Okay. This is a little bit too pink. I think we're pretty close to the right amount, but I'm not entirely sure. So at this point, because of the nice pink color we have, we know we're right close to where the moles of acid we started with is equal to the moles of base we added. Of course, I could go, so this is what we call the equal molar point. If I add a bunch more base, I can make this dark pink color. And at this point, I don't know how much excess base I've added. I just know that I'm excess. I don't know how much excess, but I know I'm excess. So let's go ahead and do this titration again. I also didn't accurately measure the amount of acid I put in. I just kind of poured some in. And that's where we're going to be introducing our next piece of glassware. And that is this piece. This is a volumetric pipette. It's tall, so it's hard to get in the shot. This piece of glassware is a very carefully calibrated piece of glassware where if we fill it up to that exact line, it will deliver exactly 5 milliliters of whatever we put in it. So if we know exactly how much acid we put in, and we can figure out how much base we put in, we can figure out the moles of each thing, as long as we know the molarity of one. So here's our more accurate run. In the flask down here, I have exactly 5 milliliters of acetic acid, or of vinegar, which has an unknown concentration of acetic acid in it. In the burette up here, I've got sodium hydroxide, which thanks to the staff here in the chemistry department, I know the sodium hydroxide in there is exactly 1.191 molarity. So if I know the volume I put in and the concentration I put in, I can figure out the number of moles of base I put in. And if I know the number of moles of base, if I stop at that faint pink, I can equate that number of moles of base to the number of moles of acid, taking the mole ratio into account. Let's go ahead and do that. So once we start getting to that point where it's close to the equal, oh, maybe I went too far. Let's give it a sec. Remember, in everything we write down, we're not writing down rate of reaction or anything like that. So that's a little darker, but it's lightening up. I would say that's a pretty good equivalence point, equal moles with the mole ratio taken into account. So now I'm going to go ahead and figure out exactly how much I put in. So I'm going to look at the burette here, and you can see I'm down at 17.123. I'm at bottom of the meniscus. I'm at 17.5, almost exactly. So I delivered 17.5 milliliters of base. I'm writing that down. We'll do the calculation in just a little bit on the whiteboard. But before I go and do the calculation, I want to repeat this process to make sure that we get, a similar answer. If I do it once, maybe it's good, maybe it's not, I don't know. But I'm going to go ahead and do this again, and I'll do it on fast forward so you don't have to watch it the whole time. Okay, so that time I got 14.8 milliliters. I had a couple mistakes there. I'm going to do it once more since I got something that didn't match. One of the mistakes I made was these three-way bulbs can be really frustrating to use, and I accidentally pulled liquid up, and so I didn't put exactly 5 milliliters in. And then I forgot to put the indicator in at the beginning. That shouldn't make a huge issue. But, and here we go. We want to get reproducible data. So we're going to keep doing this until we get something that makes sense. Okay, there is our persistent faint pink color, much closer to the equivalence point because I've got that really nice faint pink. And this time it is 17.45. So clearly that second trial was a mistake. And it's about 17.45 milliliters, 17.5 milliliters of the 0.191 molar sodium hydroxide to neutralize, we can do a little bit more, to neutralize the acid. That is to say, to get equal number of moles of acetic acid to base added. We'll do the calculation separately. Those of you who noticed that I was putting water in, that's really just to make it so I've got a better observable volume. But adding water doesn't affect the moles of acid, so it doesn't actually change anything in terms of the stoichiometry that's going on. That's what a titration looks like. If we wanted to get a full titration curve like you would in Chem 126, 129, you would collect data throughout, measuring the pH each step. We'll do the calculation in just a little bit. So here's what we got experimentally. We know because we used that volumetric pipette that we put in exactly 5.00 milliliters of vinegar. And notice we've got those extra significant figures because we were using some glassware that could measure more accurately. In order to get to the right neutral point, we had to add 17.49 milliliters or 17.5 milliliters of 1.191 molar sodium hydroxide. So from this bit of information, I can do 17.49 milliliters times 0.191 moles per a liter, and that's moles of sodium hydroxide. And I can also do this, I can divide by 1,000 milliliters per 1 liter. This will get rid of the liters. This will give me the number of moles of sodium hydroxide. Grab your calculators and do the calculation real quick. And this should be a nice reminder that stuff we did in week 1 is coming back in a big way. That's going to give me 0.00334 moles sodium hydroxide. And there's a couple things that we need to know in order to relate this number of moles to this number of moles. Thing number one. We have to stop at the equivalence point. We had to have some indication of when we're going to stop, when these moles are going to be relatable to each other. And two, we need the stoichiometry. In particular, we need the balanced chemical equation, which is going to be HCl aqueous plus NaOH. Wait, that's not what we're doing. Oh. It's inside the vinegar is acetic acid, so it's CH3COOH aqueous plus NaOH aqueous goes to H2O liquid plus NaCH3COO aqueous. And the important thing we need to know here is that it's 1 mole. This equation's already balanced. I've got my acetate, I've got my acetate, I've got my sodium, I've got my sodium, I've got my HOH in the form of water. So the important thing I need to know here is that it's a 1 to 1 mole ratio. Or that is to say, 1 mole CH3COOH is needed for every 1 mole of NaOH. Then we can take this and we can convert the number of moles of sodium hydroxide into the moles of acetic acid that we neutralized. But since it's a 1 to 1 ratio, I'm going to skip that. Well, let's still do it. Instructional videos, right? So we're going to have 0.00334 moles NaOH times 1 mole CH3COOH per 1 mole NaOH. Getting that from the chemical equation, knowing that for every mole of acetic acid, I need 1 mole of sodium hydroxide. And you can see why I wanted to skip it. Mathematically, this is really boring. You're multiplying by 1. Chemically, however, this is quite important because that mole ratio, essentially the recipe for the reaction, the chemical reaction, gives us a way to relate one reactant to another or one reactant to a product. So we can use this to convert from talking about sodium hydroxide to talking about moles of acetic acid. Again, through the stoichiometry. 0.00334 moles. Follow the units. Na always cancels out. CH3COOH. Cool. So now we know the number of moles in our vinegar, and to get our concentration, it's just going to be that number of moles over this volume converted to liters. So we're essentially going to be doing the same thing backwards. 0.00334 moles CH3COOH in 0.005 liters. And before we calculate this, we should know that the vinegar is going to be a higher concentration than the sodium hydroxide. Because to get an equal number of moles, we needed more volume of sodium hydroxide than vinegar. So when we do this calculation, we get a concentration of 0.668 molarity acetic acid. You notice we also have to be really careful with our labels at this point, because in this problem, we've got 2 volumes, we've got 2 molarities, and we got 2 moles. So it's really important that we're careful with our labels so we don't lose track, right? When I write 0.668 molarity, I usually like to write acetic acid over what is it the molarity of. When you do this for your experiment, you're going to have to do it with your numbers, but this is the general process you should be using.